Hello, everyone, and a very warm welcome to today's webinar. We are glad that you're able to join us today. My name is Gabriel, and I'm the Offshore Business Manager here in Bureau Veritas, Singapore. Just an administrative announcement before we get started. We'd love to hear from you. Therefore, if you have any questions during the presentation, please do not hesitate to raise your questions through the Q&A function, and we'll endeavor to go through them at the end of the presentation. Today's webinar is titled Ammonia, Membrane Tank, and Alternative Fuel. Well, our maritime industry is exploring alternative fuels, including ammonia, in our effort to reduce the environmental impact and to also find new ways to limit carbon emissions to meet IMO's ambition. So one of the key ways to achieve this is to use alternative fuels such as ammonia. There are indeed a multitude of advantages, but we definitely have to address the challenges ahead of us. Today, we are glad to have two excellent presenters with us to address this topic on ammonia. We have Mr. Julien Boulland from Bureau Veritas and Mr. Stephane Maillard from GTT. Our first speaker is Julien, who is the subject matter expert for gas within Bureau Veritas Marine and Offshore for the South Asia region. His work covers LNG, LPG carriers, FSRU, LNG bunkering, LNG and alternative fuels such as ammonia, methanol, and hydrogen, etc. Julien joined Bureau Veritas about 15 years ago with 6 years in Paris head office and 9 years in Singapore. He holds an MSc in Maritime Engineering Science from UK and an engineering diploma in France. For our second speaker is Stephane. Stephane graduated in Naval Architecture and Offshore Engineering in 2006, and he joined GTT as an R&D engineer involving in sloshing calculations and the design of membrane-type LNG carriers and offshore units. He's currently the general manager of the newly established GTT subsidiary here in Singapore, covering commercial activities in Southeast Asia, Japan, South Korea, and Australia. Stephane is a member of the working groups of the Singapore Technical Reference TR56 for LNG bunkering, and he has also participated in the first LNG bunkering vessel project, which is now currently under construction in Singapore for Pavilion Gas. But before I pass the time over to our speakers, we would like your participation with one poll question that will be shown on your screen. Right, the question will be, do you think that ammonia is a very attractive fuel option of the future that the industry should progress towards it? Well, some people might say, yes, definitely, or somewhat agree. Well, others might say, maybe, we're still sitting on the fence because there are many other contenders and there are no emerging leaders as yet. Or others might say, I somewhat disagree, or maybe even totally disagree. All right, just have a few more seconds. A lot of people are putting in their poll. All right. Okay. Well, people still coming in. We have quite a bit of attendees today, so give us a little bit of time. All right, let me end the poll and let me share the results. Okay, so we can see here that, well, we can see that most people here think that ammonia is likely to be the fuel of the future, right? And yes, I think that ammonia is indeed promising and have much progression towards this reality. So, well, we thank you for your active participation in this poll. And now I shall hand the time over to Julien for his presentation. Julien, please.
Yeah, I share my screen. Okay, share it. Hello. Can you hear me, Gabriel? It's okay.
We can hear you.
Okay, thank you. So welcome everyone. Thank you, Gabriel. So my name is Julien. I work for Bureau Veritas as gas specialist in the Southeast Asia region based in Singapore. So in this next presentation, I will share with you on ammonia as a fuel and what we do in Bureau Veritas. So basically, for the marine and offshore industry, we in Bureau Veritas provide classification, certification, statutory compliance services, and we provide consulting through our BV solution line of services. and we are your trusted partner to achieve safety and environmental compliance for a wide range of ship type. So the agenda for today, so before we jump into ammonia as a fuel, which is the topic of this webinar, I would like to share with you maybe the larger picture of alternative fuel for shipping. Then in the second part, moving on to the properties and characteristics of ammonia. So we wanted this webinar to be as informative and technical as possible. Then in the third part, I will share with you what we do in Bureau Veritas regarding ammonia as a fuel. So we are about to release soon in July new rules on the usage of ammonia as a fuel on board ship. So we, in our role to support the shipping industry and support innovation, we in BV have worked on the development of these new rules. So please stay tuned if I may, and I will share in this presentation on the key principles and the content of this new rule note. And then in the last part, the fourth part of my presentation, I will share on another notation that is called ammonia prepared. That also will be released this year, very soon in July as well. So in the scope of this ammonia readiness, we have worked together for GTT. So ammonia preparedness basically gives greater flexibility for ship owners that are, those intention are to go to LNG and ammonia. So at this juncture, I would also like to thank GTT for their trust and for the work that we have carried out for them on this ammonia preparedness. And I would like to thank GTT and in particular Stephane for co-hosting this webinar today. So the next slide is on the IMO and EU regulation. So basically what we see on this timeline are the various efforts at IMO and EU level to first monitor and then regulate the various greenhouse gas. So greenhouse gas, it's 6 gases. So we have CO2, methane, N2O, and 3 oil-based gases as per the UNFCCC process. So then let's have a look at the so-called IMO greenhouse gas goal for 2030 and 2050. So basically in 2030, it will be required for a ship to be 40% more efficient in terms of CO2 emissions. So a 40% reduction in CO2 emission compared to 2008 level. And in 2050, it will be required for the same ship to be 70% reduction in CO2 emission compared to 2008 level. And then overall, IMO, they would like a 50% reduction on all greenhouse gas. So why we have 50 and 70 is because it's to cater for a likely increase of the overall number of ships. So that means individually, ship, they will have to be super efficient in terms of CO2. So it doesn't come in one go. So the various effort in the past decades is a continuous process to achieve these goals. So in 2018, the IMO has adopted an initial so-called strategy on greenhouse gas, setting out a vision which confirms IMO commitment to reducing greenhouse gas emission from international shipping and to phase them out as soon as possible. So this strategy will be revised in 2023. So the IMO has identified 3 main pillars for this greenhouse gas reduction, which are first, ship design. How do we make ship more efficient? 2, operational measures. How do we basically reduce maybe the CO2 emission through operational measures? And the third pillar is alternative fuel, and this is the topic of today's webinar. What we see on the timeline is basically ship design is covered by this so-called EEDI, Energy Efficiency Design Index, which applies to a new build ship. So the phase 2 was in 2020, the phase 3 will be in 2025. In 2025, it will be required to have the 30% reduction on CO2 emission. The other measure you see in 2018, it started, are basically the recording and monitoring of the fuel oil on board, and with indirect calculation to determine the CO2 emission. Basically, the idea of this is without any data, we can't have a proper policy. So we need to have accurate data to rely on to set the policies. Now, moving on to alternative fuel to meet the IMO goal and the decarbonization of the shipping industry. So on this slide, we have put basically the storage characteristic of the candidates for alternative fuel. So we see the LNG, it's there. So LNG, I would say, has been developed for the past 20 years. We all know it's a very mature technology right now. It's available globally and it's widely used on board a vast variety of different ship type and ship size. What we see here is also ethanol and methanol, which are also under development to be used as a ship fuel. We have liquid propane, which is a constituent of LPG, which is also in development. And then we have the ammonia, which is highlighted in red, and hydrogen that we see in this two form, which is liquid and compressed. So when we look at the ammonia, here it's expressed when you look at a particular parameter, which is called volumetric energy density, that basically tells us how much energy it can carry in terms of volume, which is important when we are talking about ship design. We see that liquid ammonia is only 1/3 of diesel oil. So I would say it's a disadvantage. So we need basically to carry 2.9 times, the storage would be 2.9 times bigger to carry the same amount of energy. So Stephane from GTT will further share on this aspect of the storage. So the great advantage, on the other hand, of ammonia is that it can be stored at a relatively high temperature in its liquid form. So basically, it is liquid at atmospheric pressure, so 1 bar at minus 30 degrees Celsius. And we have a storage at 10 bar at a temperature of 20 degrees Celsius. So by the way, ammonia, if we want to remember something, it's very much comparable to propane in terms of gas, liquid, pressure, temperature diagram. So let's have a look at what we do in BV. So again, is the broad picture on all the alternative fuel. So when we focus on ammonia in the middle, so as I said, we are going to issue the NR 671 in 2021. So it will be a new rule that covers ammonia as a fuel. When we look at the work at the IMO level, there is no, it's not a work item right now, ammonia as a fuel at the IMO level. So IGF that cover low flash point fuel, there is a provision for alternative design. So we can use this one to cover ammonia, and we can also use IGC for the storage. The other fuel, alternative fuel you see on this slide, we have LNG. As I said, it has been developed for more than 20 years now, so it's mature. So we have guidelines and rule notes, sorry for that. We have the IGF code at the IMO level. LPG is also, we have worked on it in BV, so we have NI 647 to cover this, this fuel. Methanol also will release a rule note in 2021, and fuel cell as well. So again, please stay tuned. Everything is available on our website. Now let's have a look at the characteristic of ammonia. So ammonia basically is this molecule. So it's toxic, unfortunately. It's a colorless gas, which is liquefied for storage and transportation. One of the features, it's very strong smell, pungent smell. That is, I would say, not a hazard feature, but it's something to consider when we will design engine room and fuel gas supply system in order not to incommodate the crew. The smell is something to consider. So it's not a safety hazard, but it's something to consider definitely. So the combustion of NH3 does not produce carbon. That's why it's considered in the decarbonization of the shipping. So basically, one molecule of ammonia reacts with oxygen, and then it produces nitrogen and water. Also, a possible byproduct of the combustion is the production of NO2, which is a pollutant. So this is something we need to be aware of, and we need to mitigate. So, and NO2 is bad. The rest is okay. When we look at the production side, also some figure, right now globally, we produce approximate 175 million tons. So just to put that into perspective, when we compare to the amount, I mean, the bunker amount, the figure is roughly 270 million tons per annum, which is used by the shipping industry, equivalent oil. So just give an idea of if, of course, ammonia is to be considered as an alternative fuel, we definitely need to ramp up the production. So right now, ammonia is in its vast majority is used as a fertilizer. It's also used as a chemical precursor for the nitrogen atom. It's also used as a cleaner and for refrigeration. So it's liquid at minus 33 degrees Celsius at atmospheric pressure. In terms of flammability, the range is quite narrow. It's 15% to 27% in terms of air mix ratio. So it doesn't burn that easily in air, and the flammability range is, I would say, quite narrow. That's the reason why up to, I would say now, it was not really recognized as a fuel because of the difficulty to burn in air. So it has a relatively low heat of combustion. So all this, I would say, feature is something that is, I mean, that are the challenges or the consideration, I would say, when developing engine. It has a low laminar burning velocity, a high auto ignition temperature, and a narrow flammability range. That's why to burn ammonia in itself, we will need to add more heat and we need to add pilot fuel up to 20% to make it burn. So I would say also to take the words of one of my colleagues, he said it's both a blessing and a damnation. A blessing in terms of safety because it doesn't burn so easily, but not so good. A damnation when we consider it as a fuel. I mean, we are all engineers, and from an engineering perspective, it's always interesting to take a look back. So we have put on this slide like some of the projects that have been done using ammonia as a fuel. So here we see there have been some projects in the 90s. So ammonia was not used as a fuel; it was used as a working fluid, basically using the cold energy for vaporization and using the gas to produce rotary motion. So it has been used to propel a locomotive and a streetcar in the UK and the US. Ammonia then has been used in internal combustion engines. So during World War II, ammonia was used to power buses in Belgium. Apparently, they run more than 100,000 kilometers. So that was during this period of time when there was a lack of fossil fuel. There was issue with unburned ammonia. So all this project, when we read the literature, all this engine, they always carry with them some a strong, I mean, smell. We can see, I mean, smell them from afar. So this is definitely one of the topics that will need to be addressed when developing ammonia as a fuel. Then other project in 1981, a Canadian company converted a private car, a Chevrolet, to operate using ammonia as a fuel. And in more recently, in 2007, University of Michigan, they have developed a pickup that you see here in yellow, actually using a mixture of ammonia and gasoline that drove from Detroit to San Francisco, 4,000 kilometers, and only requiring one fill-up. I like this example because when we will be talking about engine, when we are talking about four-stroke engine, definitely there will need to be a mix. Ammonia cannot be used only by itself. So probably using of ammonia in the first, I would say, phases will be probably together with a conventional fuel. And other example here is space transportation. So it's not entirely relevant because the engine is totally different to land transportation, but it just to say that we have used ammonia as well for space transportation. The production of ammonia, so as I said, is one of the most produced worldwide inorganic chemicals. We have 4 countries that are producing that cover more or less 60% of the worldwide production: China, Russia, USA, India. So the production of ammonia make use right now, I mean, in this industrial form, make use of a so-called Haber-Bosch process. So basically, we have a molecule of nitrogen, but 3 molecules of hydrogen, and then we produce 2 molecules of ammonia. So this industrial process is basically operate at moderate temperature, 450 degrees Celsius, but very high pressure, 100 bar. And this process right now in its form is very highly energy intensive. So that means on the production side of ammonia, definitely it's not carbon free. There is a lot of carbon that is produced. On the combustion side is okay, it doesn't produce carbon, but production side, definitely we have to work on it. So this is why on this slide we've put, and we thank JGC Corporation for this, the so-called brown ammonia, which is the current form of production, the blue ammonia, where it's a bit better in terms of if we can capture carbon during the production through a carbon capturing scheme, we can improve the carbon footprint of the production. And then the next phase will be the green ammonia, whereby it's produced out of renewable sources. Then we have fuel cells that produce H2, and then in turn we produce ammonia. So it's still a long way to go to produce carbon-free ammonia. Nevertheless, so let's come back to shipping. To transport of ammonia at sea is a long story. It's been done for many, many years. So ammonia, again, not as a fuel, but as a cargo, it's entirely covered by the IGC code. IGC code is the code for the construction of liquefied gas carrier. So basically, ammonia is transported on board the LPG carrier. either in a fully refrigerated form at minus 33 degree or so-called semi-pressurized, semi-refrigerated at a, let's say, maybe a temperature of 20 degree or 40 degree. So here we have an example of an ammonia carrier, a 22,000 cubic meter LPG carrier. So as I was saying earlier, ammonia, when we look at the curve, the liquid gas diagram, pressure temperature is very much similar to propane. Yeah. Then going to ammonia as a fuel, it requires the amount of minimum ignition energy that is required to burn ammonia is quite high, and it's of several order of magnitude higher compared to carbon-based fuel like methane, LPG, and methanol. So that's why we need to bring energy, more energy in the combustion engine to burn ammonia. Also, the flammability range is different. So this is also, something to consider when we develop engines. Now let's have a look at the characteristic, the toxicity, environmental impact. So ammonia, which is good. I don't know if it's good or bad, but it's lighter than air. That's what we read when we read the LPG carrier operating manual. Basically, all the other gas that are transported by LPG carrier, they will tend to be heavier than air. Ammonia is lighter than air, so it will go up. However, when the air is saturated with water, high humidity, ammonia will be heavier because there is a formation of ammonia vapor cloud. So it will, on the other hand, drop down when it's in a humid air. Interesting feature, which is one of the, I would say, pillar of safety with ammonia. It's a very high solubility in water. We can dissolve ammonia in water. And we can't, for instance, dissolve gas that easily in water, but ammonia is easier. So that explains one of the safety features about ammonia, how to mitigate the impact of ammonia release. When we look at toxicity, as I said, it can be smelled by a human at a concentration of 5 parts per million, 5 ppm. So actually, we can detect it before it becomes dangerous or lethal. At 30 ppm, ammonia starts to be dangerous. So this is important, these two concentration 5 and 30, this is also something we have put in our rule for ammonia as a fuel. We have detection at 5 and detection at the 30 ppm. 30 will launch basically a water mist system to capture ammonia. And then above 100 to 200 ppm, depending on the exposure time, ammonia has irreversible health effects. In terms of environmental impact, global warming potential 0, it's good. Ozone depleting potential 0, also ammonia is good. But on the other hand, it's quite bad for marine life. As I said, it can dissolve in water and then it can cause a poisoning of marine life when the concentration of ammonia is too high. And it's also something that we have put in our guidelines. It's also when we capture ammonia with water, we also need after that to monitor and control the concentration of ammonia in water before we can discharge outside. The other toxicity is the byproduct of combustion. So NOx, as I said, we can produce NOx, NO, and NO2 by burning ammonia. So we have to be aware of that. Ammonia is also dangerous and also it's a pollutant and it's regulated by the IMO. So we have to control that. We have also ammonia unburned ammonia slip that we have to mitigate. And we have the last gas we can produce, unfortunately, with ammonia is so-called nitrous oxide, which is the laughing gas that we know. But it's a very, very potent greenhouse gas with a very high global warming potential, 300 times the one of CO2. So we definitely don't want to produce N2O by using ammonia. Sorry. So ammonia, now the corrosivity, so it's an alkali. So basically it will corrode galvanized metal, zinc, copper, brass. So again, when we are talking about engine development or fuel gas supply system or tank development, it will not be possible to use this type of metal, zinc, copper, and brass. If the concentration of nickel in alloy is above 6%, it's not possible as well. So maybe Stephane, I think, will develop also on this in the material selection. There is some material we can't use for the membrane. And then also it touches on the quality of ammonia. It's also the same topic. It's not the same topic, but we have the similar topic with LNG on the quality. If in ammonia we have the presence of oxygen in a few ppm, then it can promote stress corrosion cracking in steel. So we want also to avoid oxygen. On the other hand, iron, steel, specific non-ferrous alloy, they are resistant to corrosion by ammonia. And some rubber and polymers, they are also compatible with liquid ammonia. Talking about engine. So basically, when developing engine, we can use like LPG, LNG, engine as a basis, but we have the whole fuel gas supply system and engine has to be really thought again. Technically, sorry, taking into consideration the characteristic of ammonia that I have highlighted. Basically, ammonia cannot be used in existing Otto cycle engine, low pressure, because of the narrow flammability range and the high ignition energy required. So need to use probably diesel cycle and a certain amount of pilot fuel, up to 20%. The corrosivity on copper, nickel, plastic means like all the fittings that we have on the piping, everything, the valve that you have on an engine will have to be rethought. So material selection. One of the also basic principle is double wall. Double wall with a ventilation of the inter-wall space. One of the challenges, as I said, the problem of foul odor. This is the first step, and the next step is toxicity. So they have to have a ammonia capture system. We cannot release like gas to a certain amount of gas. With ammonia, we have to capture it and then release it. And then this is also the challenge when developing engine is also the multiple fuel supply system. Four-stroke engine, as we understand, they will have to use a mix of fuel. So probably on board, we will have to have diesel, LNG, maybe ammonia. So X flexibility is the key, we think so. And then talking about the exhaust, as I said, there might be production of NO2. So the ammonia engine right now, they would need a selective catalyst reduction. That means to capture and to transform NO2 into N2. And as I said, nitrous oxide can also be formed. So now moving on to what we've done in the use of ammonia as a fuel. So I would just go through the key principle in one slide of our new rule note. So basically, we want to prevent the leakage, to limit the consequences of ammonia toxicity. So the tank and the pipe design, they will have to be designed at 18 bar and for 45 degrees Celsius, and double wall piping will be the design principle. So we want to detect and manage the possible ammonia leakage. So this is why I was saying we will have this 5 ppm and 30 ppm threshold that will trigger various reaction in the system. And the management of the leakage, probably, we propose it to be managed through a water mist system. And then when the ammonia is captured, the design will also need to cater for a concentration reduction system. They will be required to have dedicated bilge system for the whole fuel gas supply system, so to manage possible ammonia spillage. And the control of ammonia discharge at sea. So we know when the reaction of between 3 ammonia in water and NH4, which is non-toxic, is affected by the pH, the acid level of the water, the temperature, and the salinity. So we know that by this chemical reaction, we can monitor I would say the concentration of free NH3, which is the toxic molecule in this reaction. We can monitor, control it by playing on pH and temperature. So the ship will have to have this mechanism to control the toxic, I would say, version of ammonia before it is released at sea. Corrosion prevention, we have a lengthy chapter on material selection for each and every part of the ship system that are handling ammonia. because of what I'm saying, the ammonia is corrosive on some specific material. And the containment system is based on IGC, because IGC, they have done the work of on the carriage of ammonia at sea as a cargo. So the containment system is a mix of IGC code and IGF code approach. IGF is goal-based, and then we'll also require ball of gas management system. So when this NR will be issued, of course, we can discuss more, in detail on your project, and we'll be happy to discuss more on this project. But today, I just present to you the key principles. We are involved in a various number of projects. I cannot disclose everything, but this one is with a large consortium. BV is part of it, with various ship operator makers. The purpose of this consortium is to investigate the feasibility of using ammonia as a fuel. So the hazard workshop has been done 2 years back. The hazard was supposed to be done last year, but because of the COVID, a bit of disruption. So it will be done this year. So basically, the purpose of it is to investigate the safety and operational hazard. And all this work has been, I presume, been fed in all these various companies. For as far as BV is concerned, we have used this work to feed as one of the source we have used to feed our new rules for ammonia as a fuel. And then the last bit is the ammonia prepared notation and the work that we have done for GTT. So basically, ammonia prepared will give a ship operator additional flexibility when they want to go into ammonia, but not straight away. And they may want to start first with LNG, and after that they want to go to ammonia. That's one thing, or they want to use conventional fuel, and later they may want to go to ammonia. So we have this ammonia prepared notation. So basically, to grant this notation, we will have to have a full design through a risk assessment of all the machinery and engine propulsion system. They have to have minimum arrangement on board for space reservation, ventilation, piping, taking into account the hazardous area, and structure and stability also has to be investigated. Ammonia is a bit more heavy than LNG. And we'll also give a additional, what we call a class notation or sub notation that will cover piping, engine, and tank. So now we will pass the floor to Stephane. So we are very proud to have worked for GTT on ammonia readiness. So we have given the approval in principle for the system to be used for ammonia, and then Stephane will share more in detail on the work and what GTT is proposing. So thank you very much. After this session, we can take a few questions, and obviously we may run out of time, so we'll take more questions by emails or direct conversation. Thank you very much.
Right, thank you, Julien, for the excellent and insightful presentation. Well, I shall now hand the time over to Stephane. Stephane, please. Stephane, maybe you can unmute.
No.
Yes, Stephane. Sorry, but you're muted again.
Yeah, okay, sorry.
Right.
Hi, good afternoon, good morning, everyone. My name is Stephane. I'm heading GTT Regional Office in Singapore, in charge of the relationship with our industry stakeholders in Asia Pacific. It's a great honor to be with you today. Thanks to Julien, thanks to BV for giving me the opportunity to be here and introduce to you GTT works in sustainability for the maritime industry. What you are going to see here is the experience from several pioneering projects and our innovation in order to contribute to the expansion of a greener shipping. So a few words about GTT. We are a key player in the field of liquefied gas, in particular LNG. We offer our established, secure, efficient technologies for containment of liquefied gas at low temperature, cryogenic conditions for shipping, onshore and offshore storage. We design, license, supplies membrane technologies and services that are crucial for the transportation and storage of LNG all around the world. We are about 550 employees with our headquarters in France and a few subsidiaries, with a first one named Cryovision in France, which offer innovative services to ship owners and terminal operators. GTT Training in the UK, which develop training courses for gas officers operating on LNG ship or LNG fuel ships. Commercial simulation tools as well with our GTT training team. We have 3 commercial representative offices in Houston, in Shanghai, and here in Singapore. Most recently, the group developed as well in the digital sector with the acquisition of Ascens, Marorka, and Oz Engineering. They are specialized in smart shipping, operational monitoring, performance optimization system for ships, with the objective for ship owners to achieve significant fuel saving and ensure vessel compliance with environmental standards. Finally, end of 2020, we acquired a French company, Areva H2Gen, that we rebranded Ilogen. It's a unique French designer and assembler of PEM electrolyzer. And this latest acquisition contributes to our diversification in the low carbon energy sector. And this testifies our commitment in a sustainable future. So these are, if you're familiar with GTT, you may be familiar with this kind of picture. This on the left is an LNG ship equipped with GTT membrane tank. And on the right, you see inside the ship one of our tank. So these are regular and LNG carriers that are all around the globe. We don't have only 500 of them currently in service or on order, but we have also more than 20 LNG fuel ships. And this started with what you can see here, a groundbreaking project, a successful milestone in the expansion of LNG as a marine fuel. It became a reference on many aspects. This is the world's largest dual fuel ship, largest dual fuel engine, and equipped with the largest LNG fuel tank. In November last year, the CMA CGM Jacques Sade loaded a full LNG bunker from the gas agility bunkering ship, chartered by Total and owned by Mitsui O.S.K. Line in Rotterdam. In half a day, even less than that, we loaded about 8,000 tons of LNG on board the ship, simultaneously with about 5,000 TEU of containers, as in Rotterdam, SIMOPS are authorized for LNG bunkering, thanks to proper analysis and advanced cargo loading software. So this ship are able with only one fueling to do a round trip between Asia and Europe of 84 days with a bunker tank of about 18,000 cubic meters of LNG. So this ship, the Jacques Sade, is the flagship of a new fleet of 23,000 and 15,000 TEU LNG fuel vessels ordered and operated by CMA CGM. And here you see inside these ships, both the container ship and the bunkering ship, as the bunker ship is also equipped with membrane system. So here you can see the famous Mark III membrane technology, which has been on the water for many years. It benefits from an excellent track record. And so the tank is built especially for container ship as an independent LNG section. The membrane tank installation has no impact on the standard shipbuilding schedule. And together with this, we will bring some saving on dead weight and guarantee the boil-off rate of the tank, which are key criteria for a container ship. So these two ships were built in China. They've been built in Hudong, Zhonghua, and Jiangnan Chinese yards of the CSSC group, with which we have a good relationship. And we developed similar solution with major yards in Korea, which have also a huge experience in building membrane LNG carriers for decades. Today on container ship, we continue optimizing our solutions for lower capex and even better performance. So this project, this container ship project, was groundbreaking, set a new reference, but we must also challenge the existing solutions. So we received an order from Vard shipyard of the Fincantieri group for one of the most advanced expedition vessels of the cruise company Ponant. So this first cruise project, the tank has been designed with an increased pressure of 2 bar gauge to provide some additional flexibility. So this is something we can propose today for tanks of a few thousand cubic meters. But in addition to that, on the right side of the slide, you can see 2 technologies, Type C and membrane from GTT. And initial ship arrangement was based on Type C with 2 bilob tanks. Due to the limiting shape of this kind of tank, the storage capacity was hardly reaching 3,000 cubic meter. But when we took over the project, thanks to the membrane compactness, thanks to the membrane shape efficiency, we were able to store 4,500 cubic meter of LNG, so 50% more. And in addition to that, save 100 of square meter of deck, which is the green area. So that has been as well an optimization work that we did with the yard and the owner to bring more flexibility, optimize the ship project. But of course, we had to develop a specific tank for the aft part, for the last one. And this is the aft tank, how it looks once completed. So you can see the tank slope, which efficiently follow the body line. So these are examples of work that we are doing for LNG fuel project, container ship, cruise ships, but we're also working on tankers, bulkers, car carriers projects. So these are additional type of ships that we're studying. And on the picture, you have noticed inside the tank, they look pretty similar because they use our well-known Mark III technology. So it's a technology that we introduced in the early 90s. The system evolved over the years to offer a wider range of options, deliver more and more demanding projects. So for example, for better insulation performance, we developed Mark III Flex and Mark III Flex Plus. This technology, Mark III Flex Plus, in fact, today provides the lowest boil-off rate on the market. We developed as well Mark III HD, high density version, that we use for cargoes heavier than LNG, such as LPG or ethane. So when we need to develop our projects, we will have a portfolio of solution for the technology in terms of boil-off rate or strength to optimize the project of the client. And today, this Mark III technology has crossed another step by offering compatibility with ammonia. So why ammonia? Actually, several projections give LNG as a predominant marine fuel as soon as 2040, with increasing shares of biosourced or synthetic LNG. But some projections also give ammonia a good share in the marine fuel from 2040 and beyond. Still, CO2 regulation not in place. So owners may be unsure of what to expect in the future. So LNG is often seen as a bridging solution. So today at GTT, our idea or concept is to offer a proven solution for LNG fuel now with a compatibility for ammonia fuel in a few years. So our proposal, LNG is today the only fuel available to reduce CO2 with fast return on investment. We have a potential for membrane tank to store ammonia with no or very limited cost of conversion, especially on the tank. There would be conversion on the engines, obviously. But the tank, the idea is to keep the tank as is. And by doing this, we keep the door fully open later on to either carbon neutral LNG, bio-LNG or synthetic LNG, or switch to ammonia. So we are currently working with classification societies on this. We received, as mentioned by Julien, a first approval in principle from BV in February this year. And we're also working together with engine makers, fuel gas handling makers, to have a complete overview of the conversion and ammonia ready option. And we're also working or planning to start a joint development project with some yards. So whether it is LNG, bio-LNG, synthetic LNG, or ammonia in the future, our solution, our tank solution will be kept the same. We're also working, as I mentioned in the introduction, in the digital world. Recently, so we completed our offer with the few companies we acquired. So today we're able to offer one platform, including voyage, trim, machinery optimization, with references across the various shipping markets. And we're also working on automatic reporting of CO2 emission. So that's an additional field of GTT is venturing. But let's focus on ammonia today, which is the topic for this seminar. So as a tank designer, we have to work around four main topics. On a general basis, of course, safety and reliability are at the core of our development, but we have to couple this with cost effectiveness and a solution that is to be ready to face the future. Digging deeper, we can identify four areas of attention when talking about ammonia as a bunker fuel, as already introduced by Julien. And if we look from our perspective as a tank designer, one is toxicity. Ammonia is irritating gas at low level exposure, but at very high threshold, it can even be lethal. Together with toxicity comes containment, confinement, how to monitor the tank's health and how to treat any leak of product. Third, again, as highlighted by Julien, a proper selection of material has to be made to cope with corrosivity, corrosion issues. And finally, we have to keep in mind that ammonia is not as energy efficient as LNG. So as a rule of thumb, for the same cruising range, you need to store twice more quantities of ammonia compared to LNG. So if you need 1,000 cubic meters of LNG to reach your destination, with ammonia, for exactly the same distance, you will need 2,000 cubic meters of ammonia. So that is a consideration to have as well when we design the project, and especially a conversion from LNG to ammonia. So let's take a look at these points. So as a reminder, the objective is to check our Mark III system, currently on the market for LNG, check its suitability to store ammonia. So corrosion and material compatibility. We have to check that our insulation system components are safe to use. Our primary container, primary buyer, which is permanently in contact with ammonia, is made of stainless steel 304L, which makes that, according to the gas code, IGC code, this component is perfectly suitable to compatible with ammonia. So contrary to other type of steel, such as 9% nickel or high manganese, there is no doubt today that our primary buyer is compatible to store ammonia. Similarly, we conducted compatibility tests with other materials of Mark III, and we did not find any showstopper. Secondly, toxicity and containment. So this is one very specific particularity of GTT membrane system. We use is the use of two buyers in the architecture of the tank. So on the picture, you can see here the two buyers, one in red and one in blue. So the red one is the primary buyer. It's permanently in contact with the liquid and the gas. So it's the stainless steel buyer membrane I presented in the previous slide. And the blue one is a backup. In addition to that, we propose to have also the hull as an additional buyer, so the gray line on the picture, similar to an LPG ship, for which you usually consider the hull as a secondary container. So the steel grade, the consequence of this, the steel grade of the hull structure shall be compatible with ammonia temperature at -33 degrees, which is not complicated feature to implement. This is what's done on an LPG ship today. By doing so, we end up having a very robust way to contain any pollution, any leakage of ammonia, thanks to these successive bias between the product itself and the environment. On top of that, each space between these bias are inerted with nitrogen and are monitored. So we can safely treat any ingress of gas, as we can collect the gas that is potentially intruding inside the insulation space. So we can detect, monitor, and treat any ingress, so which provides a high level of safety for the storage. So these have been pillars of our ammonia-ready concept that we developed. So as mentioned before, we received from Bureau Veritas this AIP, testifying the suitability of Mark III system to carry LNG and ammonia. So at design stage, I insist, at design stage, this notation can be selected. And then as a designer, we will implement a few elements. So One is the steel grate of the hull supporting the tank, and some reinforcement related to the density of the cargo. As you may know, ammonia density is higher than the one of LNG. So this has to be taken into account in terms of strength of the containment and the hull scantling. So I will illustrate with some example later how we do this. So this has been an AIP we received in February, in February this year from BV. But if you remember, I mentioned 4 considerations for tank designer: toxicity, corrosion, containment. So these 3 have been explained and sanctioned in this AIP. And the last one, the energy density, it's not a technical matter per se, it's an operational consideration. So I would like to illustrate this with 2 examples. The first one is an application to container ship. So that is an example on a 15,000 TEU vessel, which is quite popular size these days. So we are used to locate the tank under the accommodation and sacrifice one adjacent container bay, either in front or behind. And we reach typical a volume of about 12,000 cubic meter, sometimes a bit more, such as 14,000 cubic meter. So we locate the tank here. It's the blue square on the top picture. But let's compare the solution for a pure LNG dual fuel vessel versus LNG dual fuel with ammonia ready tank. So on the bottom picture, you can see in blue the tank shape for a pure LNG dual fuel ship. For an ammonia ready tank, which is in green, you can see that we are slightly adapting the tank shape, narrower, taller, and we will also increase the insulation strength to cope with the density of ammonia. So you can see in blue, the foam density would be 170 kilogram cubic meter for the Mark III system, while in case of ammonia ready tank in green, the foam density would be increased to 210 kilogram cubic meter. So you can see how we use our Mark III portfolio to design and optimize the tank according to the application. But in any case, we will keep the same overall volume. These 2 shapes, when you multiply by the length, still keep a volume of 12,000 cubic meter. So which makes that later on, when the fuel is switched from LNG to ammonia, the cruising range will be divided by 2. So bunkering activity will be doubled, or the bunkering infrastructure shall be in line with this as the bunkering process will become more recurrent. So to solve that issue, we could think about doubling the tank size, just multiply by 2 the tank size, and then no issue when you switch to ammonia. But you can imagine in practice, this will impact too much the container space, which in the end will be a loss of revenue for the owner. So we are not considering this option today for container ship. The same volume will be kept and more bunkering activity. But on the contrary, if we look at this second application to a Newcastlemax, a bulker or Newcastlemax in particular, here we can see a different strategy. Usually, in the recent project, you can see in the press, LNG dual fuel Newcastlemax have regularly a specification, a tank capacity of 6,000 cubic meter. The background behind this is 6,000 cubic meter is roughly the volume required on LNG for 2 round trips between Australia and Far East Asia. But technically, it is also the maximum size for Type C tanks on such ships, because the space required on board with 2 tanks, 2 Type C tanks of 3,000 cubic meter, take a lot of space and the half part of the ship. And there is a limitation, which makes that it's very hard to locate more than 6,000 cubic meter with Type C on a Newcastlemax on the half part of the ship. But if you remember the cruise ship project, membrane system is more compact, is much more space efficient. So here, for Newcastlemax, we will use the same advantage. Thanks to our modularity, we are able to install a tank on a Newcastlemax behind the accommodation. We are able to install 7,500 cubic meter of storage capacity. Still no impact on cargo because of the tank location. So we are, I would say, we can afford to make bigger tanks on the ship. because there is no impact on cargo. But this makes that we have, by increasing the tank size, this makes that we have a much more versatile vessel. Indeed, with 7,500 cubic meter, this volume is good enough on LNG for 3 round trips between Australia and Far East Asia. So it means less bunkering operation, less diversion to the bunkering port. So in the end, savings in terms of operating expense. And this volume is also enough on LNG for 1 round trip between Brazil and Far East Asia. So this kind of vessel with this size of tank is no more a prisoner, should I say, of the Australian trade only, because you can reposition the ship on another trade with sufficient autonomy, sufficient cruising range for a longer trip. So that is on LNG and some advantage on the LNG side. So what about ammonia? Again, cruising range will be divided by 2 when you switch. So on the Australia Far East Asia trade, you end up having more than a round trip on a bunkering operation. So this gives a lot of flexibility because you are above 1 round trip. And on a Brazil Far East Asia, here on ammonia, you have enough on one-way trip. While if you have only 6,000 cubic meter, when you switch to ammonia, you don't even have enough to do a one-way on ammonia between Brazil and Far East Asia. So you can see here the strategy for Newcastlemax from our point of view will be different from the container ship I presented before. Here, we would suggest to increase the tank capacity, make the ship as flexible, as versatile as possible. So this shows how we can play around as a tank designer to answer ship owner charterer issues. We have various tools, approaches to define the most efficient way to answer to the decarbonization agenda. So how can we help? If you're a ship owner or a charterer, we can assist throughout the project from the concept, as I illustrated before, up to the first bunkering operation. We provide all the engineering, on-site supervision during construction, services during the ship's life. So don't hesitate. We are here to help you, and we will be happy to help in your journey. Thank you very much.
All right. Thank you, Stephane, for the excellent and informative presentation. We'll now come to the Q&A session to address some of the questions that are raised by the audience. May I invite Julien to come on, to turn on your video, and Stephane too. Yep. Okay. All right. Maybe I'll direct the first question to Julien. Julien, you have presented on the various alternative fuels and compared them to their various characteristics. So since there are quite a lot of interest in both ammonia and hydrogen at this point in time, in your view, which fuel is likely to be leading in terms of maturity? Julien, you're on mute.
Yeah, thank you for the question. Now, as we were saying, I mean, LNG is mature. It's been there developed for 20 years. Now it's mature. So we believe it will be a so-called bridge fuel, maybe for the next decade, because it definitely provides, advantages in terms of CO2 emission, 20% less compared to a conventional fuel. Then talking on the next generation, whether it's hydrogen or ammonia, definitely, as I was saying, it will be probably a combination of fuel. Flexibility and mix will, maybe will be the solution. Also, it comes with CAPEX, it comes with OPEX. So also we have to understand that as an industry. On the technical bits, probably ammonia is more ready. We know engine maker, they are working on it. Fuel, the containment system is there. The fuel gas supply system also, as we say, we're all engineers. There is a technical solution. So from a technical point of view, ammonia probably is more ready. Hydrogen would be probably later, yeah.
All right, great. Thanks for your point of view on this matter. The next question maybe to Stephane. You presented on the application of NH3 ready notation to container ships and Newcastlemax. Are you able to share with us what is the kind of feedback from your customers regarding NH3 ready option for membrane tanks?
Thank you, Gabriel. Well, we introduced this concept early this year in January, February. And we had quite a positive feedback already from owners and charterers. Some of them have already made some inquiries as well to shipyards to look at the modification and the associated cost. Because in fact, having after a certain point, membrane tank makes sense for LNG and ammonia due to the size of the tanks which are required. So we have quite positive feedback from the industry so far. So we are developing other options, other ship types. So we have quite a good positive feedback.
Right, thanks, Stephane, for sharing with us on the positive feedback. All right, the next question, maybe to Julien, says, in terms of energy used and carbon emission in current brown ammonia production, how advantageous is ammonia when compared to HFO and LNG from well to exhaust stack of ship?
Yeah, when we look at the whole life cycle from well to wake, I mean, ammonia, we know in the current state of manufacture, it produces a lot of carbon. So it's definitely not carbon free. It defeats the intention. So this is why the next step will be blue and green ammonia with the production of ammonia on a more less carbon intensive basis. Yeah. But it's a general discussion, not only for shipping, it's for the whole, human activities. But right now, brown ammonia, a lot of carbon, definitely. What I'm saying is that the sooner the industry, the shipping industry is developing ammonia as a fuel, then it gets ready, and then we'll leave the production side also to, do their own, technology development to be more carbon free.
Sure, thanks. I think we have the importance of having green ammonia. Okay, the next one for GTT, I'll combine two questions, is quite technical. What is the maximum pressure of these GTT tanks for ammonia that ammonia can sustain? And then the other one is, should the NH3 bunker tank be at the cargo area?
Okay, so for the first question, standard operating or maximum operating pressure for a membrane tank is 700 millibar gauge, which is the standard today for all our LNG fuel projects, except some exception, like the cruise ship for Ponant, for which we have an application up to 2 bar gauge of pressure. So depending on the application, we will suggest either one or the other based on the tank volume, based on the application. So this, by default, I would say 700 up to 2 bar gauge if needed, or we have also some version at 1 bar gauge, for which we had also an AIP from Bureau Veritas. So we have again a portfolio here to cater for each specific project. And the second one, can we locate the ammonia tank in the cargo area? Yes, there are codes, of course, to fulfill regulations, but unlike the container tank, the tank would be located part in the cargo area. So this is a possibility. You have some segregation to apply. So all these are guided in the rules.
Right. Thanks, Stephane. Okay, the next question for Julien maybe says, does BV allow water that contains ammonia discharged to the water? If yes, what is the maximum NH3 content that can be discharged?
Okay, so just one thing, I see that we have loads and loads of technical questions, so definitely we cannot answer all of them, so we'll be happy to answer later and to engage more in discussion with you. So we take a few technical questions. On this, the toxicity basically of dissolved ammonia, as I said, is mainly due to the presence of the free form of ammonia, NH3, in the water. And this free form is affected, as we say, by the acidity, the water pH of the water, the temperature, the salinity. More basic and less temperature, they will decrease this content. So basically in the rule notes, what we have done is we have set the principle. We explain that it can be a way to reduce the free form of ammonia before it's released into the at sea. However, for the limits in the effluents to be discharged, we don't set the limit, and probably it will be set by recognized body and probably by coastal state, and will follow the usual IMO procedure for each and every party to agree, and probably local regulation. But in the BV rules, we set the principle of reduction. We explain how we can reduce the toxicity of ammonia before releasing it at sea.
Okay, thanks for the explanation, Julien. The next one for Stephane. Question is, as fuel is continuously being used, LNG or ammonia, are these tanks good for sloshing at any ullage level in the tanks? Needless to say that these tanks are located very high, effect of ship movement is accentuated. I think something along the location. Yeah, thanks.
Yeah. Sure. So that's a very good question. It is, of course, we have to design the tanks to be operated at any filling level with membrane. And this is made completely for all our LNG fuel projects. So the container ships, the cruise ship, even our bunkering ships are designed for that. So they can sail all around the world with the proper insulation strength. All this is made at design stage or even concept to make sure that the tank can withstand any filling level in the tank. So we have a dedicated team for this and a laboratory in France. So I was initially in this team before joining the commercial team. So we have quite advanced tools to validate the tank location, the tank shape, the tank strength against sloshing loads. And all these are then submitted to the classification society so that they can review and approve the drawings that we submit for the construction. So of course, yes, our container ship, all our LNG fuel project, similar to what we do for FSRUs as well, and the FLNGs, which are also ships which have been operating in partial fillings with membrane tanks already. Exactly the same principle.
Okay, thanks for the explanation. One more question for Stephane. I think it's regarding the slide. If I'm not reading the question wrongly, it's like, why is the ammonia tank or the NH3 tank has to be a little bit taller? I think in your slide, you know.
Okay, yeah, it's on the container ship. Yes.
Yeah.
So this is one of the reasons. So it's to be able to deal with the sloshing effect and to manage the loads on the containment system. So ammonia being denser, having a density higher than LNG. So to limit the loads, to limit the force on the containment system with ammonia, if we make the tank narrower, then the loads will decrease. So it's a way for us to make the tank able to cope with the sloshing loads, because these are still wide tanks. So it's a way to limit the sloshing loads and design the tank to be able to operate at every filling level with LNG or ammonia. So if we make it narrower to keep the same volume, we can either make it longer or taller, but making it longer would impact the container bay. So it would impact the revenue for the owner. So we decide to make it taller.
Sure. Thanks for the explanation, Stephane. The next question for Julien. What is the recommended firefighting measure on ammonia fire? Any source of reference? I noted that ammonia leakage, it was highlighted water mist system to contain.
Okay, no, this is an interesting question. So ammonia, the first, as we said, in terms of safety, is not that bad because it doesn't burn that easily. So the first feature we want to protect against is the toxicity. As I said, the ammonia, it dissolves greatly in water. So to capture the vapor of ammonia when it's released by spillage and then it becomes vapor, this is why I said we will need to have a water mist system that capture basically the ammonia in vapor, put it back in water, and then we'll need to control that concentration of ammonia before we discharge or we do something with it. So basically, fire is less of a concern. It's still a concern, but toxicity is much of a concern for ammonia, which is the other way around compared to, let's say, gas, for instance.
Okay, thank you, Julien. Maybe one more question for Stephane. Regarding the efficiency of the tank. You say that membrane tanks give a bigger efficiency regarding space. So how do you compare these with Type C tanks in terms of space? Maybe you want to elaborate a little more again?
So obviously this is on a case-by-case basis. It will depend on the ship project, the ship arrangement, and the space we have available to implement the tank. I would say one very good example is this cruise ship for Ponant, for which in less space on the GA, we are able to store 50% more capacity for the fuel. So it's quite impressive, but that is particular to the Ponant project. For other type of ship like the bulker, the Newcastle Max I presented, we're able to stretch a few more cubic meters, 7,005 with membrane against 6,000, for example, with Type C. So of course, there is no single number, but as a rule of thumb, membrane is always more space efficient than Type C because we're squarish, we're integrated inside the hull structure compared to a Type C of its cylinder shape, which is less efficient by definition.
Okay, thanks. Okay, one last final question to Stephane. We hear some challenges when it comes to storage of ammonia. Apart from the tank, do you foresee any other challenges for ammonia as fuel?
Yes, there will be. So we have mentioned already the rules. IGF, we need to go through alternative design today to deal with the IGF. There will be very likely a need to develop bunkering standards, as we did, for example, here in Singapore with the TR56. So Julien and I were together on the working groups. So bunkering standards very likely to be developed as well for ammonia. I think there are already some initiatives in that sense. And another one will be, I think, for the crew. Crew may not be used to deal either with gas engine and maybe even less with ammonia. So crew training will be as well critical. So we faced exactly the same situation a few years back with LNG, as we trained as well the crew of CMA CGM before they took delivery of the container ship. We trained them, thanks to our GTT training team, on a simulator so that they could learn how to run the ships, gas fuel ships, before they take delivery. So that's additional consideration. The human factor, of course, is very important.
Sure. Okay. Thank you. Before we end the session, any closing remarks first, maybe from Julien and then Stephane?
Closing remark is very difficult. It's more opening remark, maybe. No, as I said, is that in BV, we'll be ready to support. Please come to us, discuss your project of ammonia. Again, we see like loads and loads of technical questions. We cannot answer them today. That's very unfortunate. We apologize for that. But we'll be happy to answer this, I would say later. So that's my closing remark. Let's discuss. Yeah. Thank you.
Stephane?
Yes, similar to Julien, let's discuss. Owner must navigate in a quite unclear future today with upcoming CO2 regulation. LNG is already doing quite good for 2030 IMO objectives. With our Mark III membrane, we can provide ammonia solution, digital solution together with the group. So we invite you to contact us, share your initiatives, thoughts, concerns. Don't hesitate. You will have all our coordinates to contact us later on. So don't hesitate. We are here to help. Thank you.
And thank you to GTT as well. Thank you, Stephane. Thank you very much.
Thank you to BV as well.
All right. Thank you, Julien and Stephane, once again for taking your time and sharing with us on the topic of ammonia. Like what Julien and Stephane say, our sincere apologies. We are not able to answer all the questions, so many of them, because of the time, but we really welcome you to email us your questions and we can follow up with you accordingly. And we've come to the end of this webinar. It's our pleasure having you with us today, and we really look forward to seeing you in our next webinar. Thank you once again.